Hello everyone, welcome to my channel. Today we are gonna continue with this series about the MIKE21 SW module, the spectral waves, and finally we're gonna run the model. Yeah, you should be happy. I'm gonna continue with the model that I was working in the previous videos. I'm gonna just open the mesh that I was working in so you know what I have been doing, but just for you to check. No. So let's open the file so you see is this mesh. As you remember, or if you have seen or you have watched the previous video, I had a problem around this area where the boundaries of this island weren't closing completely. So I fixed that, and that's the only difference between the image that I showed you at the end of the previous video and this one. Yeah, that's the bathymetry, and basically, well, what we talked in the previous video. I'm gonna close this because I'm not gonna talk about the refine the ways where how you can refine the mesh in this video. That will be in a later video probably, but I want to show you how the SW model works and is it defined, because you're gonna always have time to play with the mesh, to refine it and make it as detailed as you want. Okay, so let's close this. I'm going to go new, file, MIKE21, and then I'm gonna select this spectral waves. So this is how it looks like. How Mike works is we're gonna go through all these items, select what we want them. Maybe we're not gonna need some of them, so I'm gonna stop in every single one of them and explain a little bit what they do and what you define on them. So first, Mike is asking us the domain, basically the mesh that we should have created already. So I'm gonna open this, it loads, and you can see that automatically loads every data, the reference with the coordinates that it should be, so everything is right. Here, well, if you want to analyze your model above a certain depth, then you should define it here. By default, this is basically the maximum depth, so I want to get analyzed every single layer of water. Also, you can play with a Dayton shift. Let's say that you have the Admiralty chart uses to be in chart datum, right? So let's say that you want to work in ordnance datum, then, or because maybe your wave information is in ordnance datum, or because some other information that you're gonna include in the model is in ordnance datum, that you need to modify it here. So let's go to the boundary names. Here you can change the name of the different boundaries that we have defined. This is useful later on while defining some, let's say, from when the waves are coming from. So it will be good to, let's say, code 2, instead of calling it code 2 we can call it north, or this is north, east, south and west. That's gonna make it a little bit more clear a little bit later when we introduce data. Time, here we define basically from when to when we want the simulation to be running. So here it will be running from the 1st of January at 12 AM till the 1st of January till 12:50. We can define the number of steps, so that will define where the simulation ends. So if I define here 200, then 200, it will calculate one solution every 30, no, it will calculate the solution every second, but it's gonna give us results only every 30 seconds. And I'm gonna talk about this a little bit later, because it's important later on while defining how detailed you want your model. You need to define what is the time step interval of the calculation, and that's important because if you're running a really complex model, the calculation can take a day or an hour depending on the level of detail that you want from that calculation. In this case here, you're just telling the software that you're gonna get, well, 200 divided by 30 number of results, and this will be the time running. Why this is important? First, because you need to allow the waves to reach the point where you want the results. So if I go back here and I'm going to introduce waves from the south, I need to allow the model to run waves from this point to this point, and that takes time. It's called real time. So a wave here will take, I don't know, maybe 10 minutes to get to this point. So I need to be sure that the time that I define here is enough for the waves to arrive to the point of interest. I'm gonna leave it as 100, but play with it because, well, this depends on how you want the results. Then if I click here, well, it gives a little description of what is the model about. Then we go for the basic equations. First, what do we want? Directionally decoupled parametric formulation or fully spectral formulation? What's the difference? Well, basically, if you have a large model, let's say that the scale is about 10 or 50 kilometers, a small model will be, you will be using the directional decoupled parametric formulation. An important thing is that if you select this, the model is gonna run faster, but you cannot introduce waves because of the wind. This is a big difference, right? So I'm gonna leave it as fully spectral formulation because I'm gonna introduce wind in this model to create sea waves. But if it's not important to you, or you think that you're not gonna need it, then selecting the directional decoupled parametric formulation is gonna make your model to run faster. Time formulation. Which one to use? The quasi-stationary formulation, you need it when the forcing wind is not changing with in space or time, or if the fetch is limited, or when individual waves can be considered as independent. The thing is that the model won't take into account what has happened before or what was going to happen after the moment where it calculates the solution to the problem. If you want to know more about how these kind of problems are solved, how you predict a solution based in previous information, I'll leave a link. But basically, selecting quasi-stationary formulation will make your model run faster, but a little bit less accurate. Instationary formulation takes into account, well, basically if you're going to introduce wind, I recommend you to also select instationary formulation, because it allows a consideration that the forcing wind changes rapidly in space and time. But also basically a general advice in this case will be select one, the other, and see the results, and that will be a process of calibration of the model too. If you want to be sure, just select both fully spectral formulation and stationary formulation. Your model is gonna run slower, and then you're gonna realize that you need your model to run faster, so you're gonna start making assumptions. Good. The spectral discretization. This is how, if you're gonna introduce, let's say, a John Swab model or not, how is it going to be discretized? So now is it defined by it's gonna take into account only 25 frequencies starting from this one, and with a frequency factor 1.1. That means that it's gonna multiply 25 times 1.1 to get the maximum frequency. Again, and you can play with those values if you know your John Swab or some other formulation that you're gonna introduce. The directional discretization, what it means is that it's gonna take into account 360 degree rows, so the waves and the winds are gonna be able to come from every direction, and that 360 degrees is gonna be divided by 16 segments. If you want more accuracy, so you can divide 360 by more number of directions, so the waves are gonna be able to come from, well, the divisions that you have included. Separation of wind and wind, sea, and swell. It affects the white capping dissipation of energy. If you define this as a constant threshold, what it does is it's gonna dissipate stronger the waves that have a certain period. So this is the cut. So you define from what frequency the system is gonna be limiting or reducing the energy of the waves. This is also a method of calibrating your model. I'm not gonna separate it. This will be, as you have dynamic, because what is a maximum? Because that will depend on the period of the waves. If you're generating irregular waves, then those waves have different periods, the train of waves. If you're generating just let's say a train of waves with the same period, not irregular waves, then you can define just, or you have to define just a threshold, because the period is known. I'm not gonna separate it, I'm gonna leave it like how it is, but keep that in mind that maybe that will be a parameter to check or to modify while calibrating your model. The solution technique, these are, well, basically if you want more detail or less detail while applying two algorithms that Mike has, I will always go for the higher order, get more detail. And now we get into what you can have to define to make your model more or less accurate. You're gonna want to make this, let's say, this minimum time step, or modify this maximum time step to make your model to run faster. But this is a key thing: the modification of these parameters are gonna have a high influence on the results of your model. Why? Because basically you're defining the accuracy. I mean, I have spoken before about just changing this directionally, the couple parametric, quasi-stationary. Okay, this affects the accuracy of the model, but not as much as this. And also it can make the model to crash. Okay, so if you define the time step like really big, trying to reduce the calculation time of your model, at some point it cannot be enough. So Mike is going to tell you, well, this level of accuracy is not enough because I can be getting 100 or 1,000,000. So that's important. How do you control that is based in a number called CFL number, and you have to keep that number below 10. There's a recommendation from the manual. There is also a formulation where you can obtain that CFL number. It is a formulation where you can know by modifying this minimum, maximum time step, number of steps in the calculation, and all of this, if you're below that 10. I will add a link to the description of the video so you can calculate that number and see if your model is accurate or not. So the key thing will be to make this number as big as possible so the calculation time is reduced without important loss of accuracy. Okay, I've spent a little bit more time in this because it's important. If you have any question about it, just post it in the YouTube commentaries and I will answer it. Water level conditions. Here you can add tides if you want to keep your model simple, and or you think that the domain in time where you are defining the results, or where you want the results of your model, is small enough that the tides are not going to affect it, then you don't need to put this. If you need, then you have to define. You can define a permanent increase of the water level that will basically do more or less the same as here, as modifying the Dayton shift. So as tide changes, you can define a tide that changes in time and domain, and I'll explain what that means, and only varying in time. If that only varies in time, what it does is the surface of the water, all of it, so all the water within this area is gonna raise or drop according to the water level conditions. If you define this other option, time and domain, what you can define is that the tide here, or the variation of the water level here, is different from the variation of the water level here. Maybe if you're working in a really large area, that will be important. If you're working in a normal to small area, just define it varying in time. But again, maybe you need to define that variation in time or in space. Then how do you define the tides? So you have to create a file that contains the tide values. So I will explain how to create those files in a later video, because it's the same procedure as when you have to define the wave heights. So that will be a video for both, to define both things. I'm gonna leave it in no water variation. If you made a mistake or Mike is missing some information, it will appear as I was showing here an X red, because I'm saying that I'm gonna define something, but I haven't selected the file that Mike needs to introduce the tides. Current conditions. If you think that the currents are important in your model, you can do the same. You can define a constant current and X and Y, so you can create an oblique current or perpendicular to one of the edges, or you can do the same. You can define, if you have the file that defines the currents in the area, so you can introduce the file here and it MIKE will read it, no problem. Basically the file is a matrix containing values of x, y, and the value and direction of the current and the speed. The same with the tides. Wind forcing, you can introduce or not wind by the speed and direction, so the same. You can define a constant wind, say 12 meters per second, and a direction of 90 degrees. So, okay, it will create a constant wind across all the area with that direction. The north is here, so it will be generating winds from the south. Again, if you have a file containing wind values, you can import it here. You can also define here, see this, soft interval means that while introducing the wind, it's going to wait for a number of seconds that you define here to load the file. So let's say that maybe you can generate a model where the waves are acting, and at some point the wind starts acting in the area, so you can define here the delay. Also here you can select couple and uncouple. What does this mean? This means that if you select couple, the wind is gonna generate waves by friction, right, with the waves, with the sea surface. The thing is that the coupled will mean that the rugosity of the sea surface is gonna be also varying according to the wind that is affecting them. So that's why it asks you to define this Charnock parameter. This is also a calibration factor, so you can modify it to try to calibrate your model to make it like more accurate, where you're checking. When I'm saying calibrating the model, it is understood that while producing one of these models you need historical information, so you can check, you can replicate one of the situations that you have the data or the results for, and try to replicate it, so you know that after you have defined all these values that I'm saying that are calibration factors, you know that the results are accurate in that or comparing with the historical real information, and you can apply your model to predict new situations. Uncoupled means that the wind is going to generate waves because of the friction, but the wind itself is not going to modify the roughness of the sea surface. Ice coverage. Well, if you're working in an area that can be affected by icebergs, or ice can be generated at the sea surface, then you can, again, the same as with the tides and with the winds, where the ice is going to be, and the same, it can be changing, yes, where the ice is going to be, so the waves are going to affect the piece of ice in a certain way. Diffraction. Well, you want to take into account the diffraction of elements in your model. Again, those parameters are calibration factors. So let's say that here's your domain. and you know that somewhere here something is gonna be, or maybe let's say that you want to obtain wave information here, and you're generating waves from here. So around these edges, well, basically it's gonna affect to everything, but the diffraction of the waves is gonna be important around here and around here too. If you want to obtain the results in this area, well, then the diffraction is not going to be really important. Why selecting no or yes? Because it affects the calculation time. So if you're not expecting to have big diffraction effects, then leave it as no. Energy transfer. Energy transfer here is defined as how the waves lose energy while getting to a close. So it's another way of wave transformation. It's another kind of wave transformation. This quadruplet wave interaction represents that when you have irregular waves, and let's say that you have 4 front waves, or wave fronts, sorry, you have 4 wave fronts coming from different directions. At some point when they clash, there is a lateral transfer of energy. There is the linear theory says that it doesn't matter if you have a wave like this and then you have another wave perpendicular to it. The energy, there is no lateral transfer of energy between waves, so this wave is not going to be affected by a wave that runs perpendicular to it. Well, that's in the ideal world, but in the real world there is some transfer of energy. So those quadruplet wave interactions happen in deep waters, basically. And this triad wave interaction is more or less the same, but with 3 wave fronts, and it happens in shallow waters. So don't check both, because the energy loss that your waves are gonna suffer is gonna be a lot, unless you really know what you're doing. But if you really know what you're doing, you wouldn't be watching this video probably. So if it is important for you the dissipation of waves in deep waters, then select this one. And also, if your waves, the waves that you are introducing in the model, are irregular waves. If you're introducing just monochromatic waves, this is not going to do anything. Neither this one. It's just if you're introducing irregular waves. Wave breaking. Well, you can introduce the effect of the loss of energy of the waves while they break. So there are different ways of introducing wave breaking, and this is also a calibration factor. So you're gonna be modifying this value and this one according to the calibration that you're doing, so trying to get the solution closer to the real values that you have. There is a formulation where you can, depending on the depth, you can play with this parameter. I'll add the link too, but basically is calibration. So this changes from the gamma value changes from, or varies between 0.6 and 159 with an average of 0.8. and the alpha factor the same. So just keep in mind that while modifying this value, it cannot be anything. It will be varying or changing from 0.6 to 159. In alpha, where it can change from 1 to 2 or 2 to 5. You will see while modifying those parameters that the waves are gonna get bigger or smaller as a whole node when they can start breaking. If you're checking the area where it's in the deep waters, you're not gonna see any difference, because this only affects to where the waves break because of the depth. Bottom friction, you can introduce another loss of energy in the system by the friction of the waves with the seabed. You can introduce that bottom friction according with the Nicolatse roughness or the D50. This is basically related, and if you know some other coefficients or the values of those coefficients, then you can apply them. The easiest way is to define, if you have a bathymetry and you have sediment information, it is easier to define the D50 of the material that is at the seabed and put it here. The same. Now this is assuming that the whole area has a material with a D50 of this diameter, but maybe that's not true. Maybe the sediment size here is different than the sediment size here. Well, that probably happens. So if you have that, then you have to define varying domain and introduce here the file that contains the different sediment sizes for the whole area. Probably you're not gonna have that, because, well, if it's a small area probably, but in this really large area you're not gonna have information of all of it. So you have to make an assumption. If you have sediment information here, well, then define it as constant and define that everything is the same. The thing is that only is gonna affect to the waves that are getting close to the shore, because in deep waters doesn't really matter. The waves are not gonna lose energy by bottom friction because they cannot feel the bottom. White capping. This is another way of dissipating energy. This means maybe you have seen that in deep water sometimes the waves break and they generate this kind of, yes, it's a white foam. It's not foam, but you know, when the waves break because of the wind or because instabilities of the waves, but not because of the depth. So here is another calibration factor, so you have to play with those values, and that will only affect or basically will affect to the energy loss of the waves in deep waters. So it's not gonna affect really a lot. Probably you're gonna be interested on the wave height here close to the shore, not what happens to a wave here. So it's a calibration factor, but by modifying those numbers, you're not gonna get really big differences between the results. Structures, you can introduce structures here, so you can have a file where a part of this you can put, I don't know, something here, breakwater, vertical breakwater, right in the middle. Why is that? And why would you like to introduce a structure here and not like we have introduced these islands? Because that allows you a lot of flexibility while defining, let's say you're designing a breakwater, a really big one that goes from here to here, a big port. So you can change the alignment and see what happens without needing to modify the mesh. and well, that's time saving. So you're gonna need to create a file. You have to select this, and then you will have to need to have created a file with the geometry of the structure. And also, if you're gonna do that, then maybe it will be interesting to introduce the diffraction effects. Initial conditions, you can define the initial conditions by introducing a Jones swap or SPM or some other spectrum that you want. If you, yes, basically you can define like here the parameters of the Jones swap spectrum or those other two. If you don't have the, or if you don't want to use the spectrums, then you can use the boundary conditions. The boundary conditions, well, the boundaries of the model are these ones, something that we already knew because we have defined them, and now they're a little bit more clear because we have assigned something that was saying just boundary 1. Now we know that it's north, east, west, whatever. So now it's allowing us to select. Let's say that we want to, this boundary condition is going to allow us to introduce the waves in the system. So let's say that we want to introduce waves coming from the south. So we're going to go to here, south. We don't want a closed boundary. So how this works? Basically, if you're not going to introduce waves from the edges, let's say that we're not going to introduce waves from the west, we should define it here as a lateral boundary, and the east as a lateral boundary, and the north as a lateral boundary. What does that mean? If I select closed boundary, when the waves reach one of the edges, they're gonna start reflecting, and we don't want that because that won't represent the model. So if it's lateral, what it allows is that a wave coming from here, it will just kind of continue, so it won't stop and reflect. What else? We can define, yes, also a reflective boundary, something that you don't really want to, well, maybe you want. And then you can define the waves. Let's say that I'm going to generate waves from the south, wave parameters version 1. Here you can define a monochromatic wave train, so with a significant wave height, a peak period, mean wave direction, and the directional spreading index. The directional spreading index means that how that wave is gonna be basically spreading while approaching the coast, while being generated. So if I select this direction, the waves are gonna be generated from this direction, but also from some other directions. This is a parameter to play with. There is definitely in the manual is not quite clear how to define this number. I found some other documentation that I'm gonna leave the link on the commentaries, so you know how to modify this number, and so you know how, while generating the waves, what is the spreading of those waves. It is not something that changes a lot the result, but if you really want to know what you're doing, then you should check that. What else can you do? If you define check wave parameters number 2, it changes. What was the first version? I think it's instead of peak period, basically it's nothing. Here you can discriminate between wind, sea generated waves, and swell. If you know that in the area that you're analyzing that could happen, then you can define if you have the data again, you can define irregular waves. So let's say that you have a void register and you have the data that boy has been recorded over a certain amount of time. You can import it here, and that's quite interesting to do. Again, well, it says constant along line or varying in time along line. What does that mean? Line. That means that the irregular waves are going to be generated from one of the boundaries. So if it's constant along the line, then all the waves generated along this boundary are going to have the same values. So let's say that even if it's an irregular wave generation, you're going to have at every point a wave of 1 meter in direction 2070. But all of them are going to be generated the same. If you generate here varying in time and a long line, then the waves here can be different from the waves here. So again, if you have that information, then you can import it here. And at the end of the whole story, outputs. We're gonna define a new output. We're gonna go here to edit it. Different things. Here it's gonna just generate an output at this point. So the only result that you're gonna get is the wave height, period, current speed, whatever, but just in this point. So it's not gonna generate map with arrows that tells you, or with wave heights. Why is that? Because that saves computational time. If you're just interested in the wave conditions at one point, then okay, you can do that. How? Let's say before I do that, here, if you want the full area to be covered with results, then you should select here area series. Here you define the output file, and this is the thing is that if you select a whole area, the waves will go through the island. So by selecting just only real wet area, it will give you just results where is not a land boundary. Here what it is asking me is to, if I select point, here is gonna ask me for the different points, so I can define another point. And probably if I change this a little bit, here it will show different point. It was too close anyway. Yes, let's change it. I don't know if I'm gonna be within the model or not. Let's see. No, I'm outside the model. Anyway, you understand what it does, right? Yeah. And well, you can generate a file with different values, so you can, instead of defining them here, you can import it here. This is the results. What do you want? Maybe you want significant wave height, but also I want the maximum. I want the peak period, the wave period, peak wave direction, well, whatever you want the results. And you can discriminate between the total combination of sea waves and swell waves, or if you're just interested in the swell waves, then you select this one, and that will give you the results only in swell waves. You can also ask the model to give you, this is the CFL number, so you should check this box. If you don't have the formulation, you should check this box and then check the results. So while obtaining the results, your CFL number is higher than 10, then you should change the here, the minimum time step. It's a good way to do it. Just do a first run, check the number, and then play with it, and some other values you want, the area or many things. Also, if you want the results of the inputs that you have introduced, then you check those boxes and it will generate a file where you obtain the well, you can check the values that you have introduced. And at the end of the story, I will be able to run the model and see the results. But unfortunately, I don't have the this is just a demo version, so I cannot run the model, and you're not gonna be able to see the results. But that doesn't matter, because basically the numbers will have been random and stuff, and once you have run the model, it is really easy to extract the results. If you want me to do that anyway, I maybe will be able to get access to a MIKE license and run it. I hope you have enjoyed it, the series, that you have learned a lot. This is I mean, it's not the most complex of the MIKE series models. Basically the one that will do everything will be the Businesque waves, but it is quite useful if you don't need to take into account diffraction inside basins of the ports. I haven't spoken about the limitation of this model, but basically use this model to get wave heights around a shoreline, but not within basins of ports, harbors or marinas or anything. That model doesn't work for that. For those kind of problems, you should use the Businesque model or some other models. Again, I hope you enjoyed it. If you have any question regarding any of the formulas, or you want me to cover a little bit with more detail any of these elements, then leave me a comment on YouTube and I'll see what I can do, because this is already 50 minutes video. Well, see you next time. Bye.